alternating method.
Yes, thank you for the very nice introduction and for the invitation to be one of the speakers at today's seminar. This is actually my first time participating in this seminar, and it's really been very interesting to hear about so much work going on in so many different areas. I'll be talking about some of my recent work in developing the Schwarz alternating method as a means for concurrent multiscale coupling in solid mechanics. And before I get into the talk, I'd like to acknowledge some of my collaborators for this work. So this is in collaboration with Alejandro Moda and Coleman Allman, who are colleagues of mine at Sandia National Labs in Livermore, California, and also Greg Flippo, who was a summer student we had a couple years back, who's currently at MSc Software in Newport Beach. Here's the outline for the talk. So this is going to be a little bit more of an applied talk, kind of like the last two that we heard, but I will touch on quite a bit of theory in the process, so hopefully it'll sort of appeal to both the mathematicians and kind of the more applied engineering folks. I'm going to start by giving some motivation and background for why we're interested in concurrent multiscale coupling and kind of why we're selecting the Schwarz method as a means to achieve this coupling. The main part of the talk is going to have two parts. So first I'll talk about our kind of early work in developing this method for the case of quasi-static problems, which is where we began the development of this method. And then the last half of this is going to focus on more recent work we've been doing, extending the method to dynamics. And so for both of these sections, I'll kind of overview the formulation, talk a little bit about the theory, and then I'm going to show a lot of numerical examples. So this is kind of an example heavy presentation, which I think really kind of demonstrate the method's performance and convergence and things like this. Okay, so let's get right into it. Motivation and background. So as I said, I wanted to kind of motivate a little bit our interest in concurrent methods and kind of also explain what I mean when I say a method is concurrent. So a lot of the problems that are of interest to Sandia National Labs where I work require us to simulate and understand the large-scale structural failure of engineered components. So for us, a lot of these are going to be components comprising weapons type systems as part of our some of our mission spaces that are kind of the bread and butter work at Sandia. For a lot of these problems, large-scale structural failure originates from a small-scale phenomenon, such as a defect or a micro crack, which grows quickly in an unstable manner and can lead to the large-scale structural failure. So an example of this would be this roof failure of a Boeing 737 aircraft pictured on the right that occurred due to fatigue cracks. And essentially, because of the very tightly coupled interaction between the small and the large scales in these types of failure scenarios, it's really essential to use concurrent multiscale methods when trying to understand and simulate the behavior of these types of engineering systems. And so when I say concurrent methods, what I essentially mean are two-way coupled methods. So methods where you have information propagating back and forth between the different scales that are involved. So this would be in contrast to kind of one-way coupled methods where you have information just going in one direction. And specifically what we've seen is that if you don't use these two-way coupled or concurrent methods, you don't always get an entirely physical solution for these types of solid mechanics problems. So our group is actually not new to developing concurrent coupling methods. They've actually been doing this kind of longer than I've been working with them. So this is a paper by my co-author, Alejandro Moda, with Steve Wei-Ching Sung, who's currently at Columbia. And so in this paper from 2014, they develop a three-field multi-scale coupling formulation that achieves concurrent coupling. So in this formulation, the third field is a Lagrange multiplier field that's added to enforce weakly the compatibility of the discretization. And so if you kind of go through this paper, there are kind of a lot of nuances with these kinds of mixed methods. For instance, how to design the Lagrange multiplier space that satisfies the INF super, the LBB condition, They were able to come up with a formulation that satisfies the condition in the paper, and the method was found to work very well on a number of problems. But unfortunately, kind of the deal breaker for us is this type of method really wasn't feasible for us to implement into some of our existing massively parallel codes that we have at Sandia that really aren't set up for mixed type methods. And so that's really kind of the motivation for this work, where we were looking at developing a method that achieves this concurrent coupling, but that would be feasible for us to implement into some of our production codes that we have. So this brings me to kind of our wish list or list of requirements for a multiscale coupling method. So I already talked about the first two bullets here. So we want the method to be concurrent or to achieve two-way coupling. We want the method to be easy to implement into our production codes at Sandia. The third bullet, so we need the method to be scalable, fast, and robust on some of the real engineering problems that we're targeting. So this is a case where, we're not just interested in developing a method to publish a paper and kind of, say we're done with it. We actually need to develop a method that could go into our production codes that analysts could use to actually, enable them to perform simulations that are, difficult to do using existing methods or not possible to do using existing methods. So ideally, the method we're looking for would provide what I'm going to call a plug and play framework that would simplify the task of meshing complex geometries. And so this is kind of illustrated in the picture at the bottom here. And I'll show this again at the very end as my last example in a more quantitative setting. But essentially, the idea here, so this is called the bolted joint problem. The idea here is that we have a lot of geometries that are held together by fasteners. That's one of the application areas that we're looking to impact here. And as you can imagine, with these fastener type of problems, you're going to have very small scales. In this case, it's these bolts or screws that are coupled to rather large scales, right? And this is relatively simple, but you can imagine this can be arbitrarily complex. And moreover, we're often interested in exploring a lot of different design configurations. So, in this case, changing the bolts, adding threading to the bolts, for instance, or, drastically changing this geometry and trying to kind of optimize it in some way. And so the challenge there is that if you have a really multi-scale object, this is very, very difficult to mesh. Even kind of meshing experts can take weeks meshing a single geometry. And so this quickly becomes infeasible if you have many of these geometries that you're looking to explore. So we're looking for a method that would allow you to decompose this into the small and large scales, mesh those two things separately, and then use the method to glue them together. And thereby, if you want to just swap out one piece for another, you can easily do that without having to remesh the whole thing in a conformal way. So with that, we're looking at a method that can couple regions with different non-conformal meshes, different element types, different levels of refinement. We're also looking for a method that will allow coupling of different solvers and time integrators for dynamic problems in different subdomains. Of course, we don't want the method to introduce any non-physical artifacts. And ideally, the method would have some theoretical convergence property or guarantee. Okay. As I mentioned, as the title suggests, we're proposing to do this coupling using the Schwarz alternating method, which is a domain decomposition method. So I'm guessing a lot of people in the audience are kind of familiar with this method, but I'll overview it nonetheless, just so we're kind of all on the same page. But this method has been around for quite some time. It was proposed first in 1870 by Hermann Schwarz for solving the Laplace equation on irregular domains. And so this was, of course, before computers. So he was actually trying to work out these solutions analytically at the time. And the basic idea of the method is if you want to solve a problem on a complex domain, you decompose the domain into simpler subdomains, and then you use the solutions on the simpler subdomains to iteratively build a solution on the more complex domain. Okay. So I'll kind of go through the algorithm really quickly in the context of this canonical picture, and you'll see this all over the talk. I have it in a number of slides. This is just meant to be a kind of a simple case just to illustrate the method, but obviously it can be generalized to arbitrarily complex and actually arbitrary numbers of domains. But let's say we want to solve a problem on this geometry that's the union of the circle and the square. what we do is we first solve the problem on the circle. So I'm going to call that omega 1. We're going to use the prescribed boundary conditions on this outer boundary. And then to get this started, you can just use arbitrary boundary conditions on the inner boundary, gamma 1. So that's not all too interesting. Then in the next step, you go to omega 2. You're going to, again, use the prescribed boundary conditions on the outer boundary. But now on this inner boundary, the gamma 2, you can take the solution you obtained in omega 1, interpolate it onto that boundary, and then use that as the boundary condition for omega 2. Okay? And then you go back to omega 1 and you repeat. And so this continues until the solutions match to some specified tolerance in the overlap region here. Oops, too far. Not surprisingly, requirement for convergence is that the size of the overlap region be non-empty. And in fact, the larger the overlap region, the fewer iterations this will converge in, so that if you have 100% overlap, you're just solving the single domain problem repeatedly, essentially. So that's an important property of the method. And so where the method is commonly seen these days, now that we have computers, it's commonly used as a preconditioner for solving linear algebraic equations. And so what kind of the new idea behind this particular work of ours was to actually try to use the method as a discretization method for solving multiscale PDEs. And even though this is a kind of a natural thing to try to do, turned out that really not that many people had really looked at this prior to when we started looking at this approximately 5 years ago. All right, so that's the motivation. So let me now kind of get into the first main part of the talk, which talks about applying the method to the specific case of quasi-static problems in solid mechanics. Okay, so at the top of the slide, I have the basic Schwarz algorithm for the case of quasi-statics. Since I think this is not a solid mechanics audience, I'll kind of explain a little bit how quasi-statics works. Although we heard a little bit about this a couple talks ago in Sebastian's presentation. So advancing things quasi-statically is a really common approach in solid mechanics. Essentially, the idea is you're solving a sequence of steady problems, and then wrapped around each problem, you have this outer quasi-static loop. And in that loop, you basically advance or increment the load that's applied to the steady system in a quasi-static manner. Okay, so that way you could do this using a homotopy continuation type of method. Usually it's incremented very regularly, but you could change kind of how fast the loading is applied. And so this is just a very common technique. So how does kind of Schwarz play in with this? So we have the outer quasi-static loop that I just explained. And then within this loop, within each steady solve, we're going to have our Schwarz loop. And so this is exactly the algorithm that I just explained a couple slides ago in words, just written in mathematical notation. So I won't go through it again. But essentially, you're just solving the problem iteratively between the two or more subdomains. Information is propagating through the boundaries, and then you continue the convergence and the iteration until the solutions match to some specified tolerance inside the overlap region. Okay. So you can see, this kind of method would have a number of advantages for coupling. It's conceptually very simple. I can write it in just a few lines and explain it in just a few words. It allows you to couple different regions with non-conformal meshes, different element types, different levels of refinement, and I'll show numerical examples that illustrate that. You have information passed back and forth between the different domains, so you get this concurrent coupling that we're interested in. We're able to use different solvers in different regions. We can use different material models as well under some conditions, and I'll talk about this in a little bit. And then it accomplishes this goal of simplifying the task of meshing complex geometries, because you can mesh the different domains independently of each other. Another kind of benefit here is that the method is based on a very solid theoretical foundation. So this is a little bit of a history of kind of some of the theory that has been done for this method, which dates back to the 1930s. So in 1936, Sobolev posed a method for linear elasticity, proved the method's convergence. 15 years later, Michelin was able to extend this result to general linear elliptic PDEs. It really wasn't until the 80s that convergence of this method for nonlinear problems was studied. So Lyon was one of the people who kind of pioneered this. He he looked at proving convergence for nonlinear monotone elliptic problems using the maximum principle. And then to the best of our knowledge, kind of our paper from 2017 that investigated convergence for the quasi-static solid mechanics is the kind of most sophisticated proof in the sense that it's for the most general and kind of challenging nonlinear equations. So we were able to show in this paper convergence of the method for the finite deformation quasi-static nonlinear PDE given by this energy functional here. And so this is basically your canonical solid mechanics problem. I think Sebastian had a version of this on his slide as well with slightly different notation. You have here A, the Helmholtz free energy density, and embedded in this A term, you have an arbitrary material model that can go from very simple linear elastic to a very sophisticated model. I wanted, since this is a numerical analysis seminar, I wanted to talk a little bit about some of the actual analysis that we did here. So this is the actual theorem we have from our paper in 2017, which was published in Kamami, and it's referenced at the bottom of the slide. And essentially the conditions for convergence of the method are that one, your single domain problem be well posed, and two, the size of the overlap region be non-empty, okay? And so I'm not going to go into the details of how we prove this. It actually takes about 8 pages in the paper. So that's what's at the background of the slide. You're welcome to look at it if you're interested. But essentially, the basic idea is we construct this sequence of functionals phi tilde superscript n. And we show that if we apply the Schwarz iteration, like I described it, to this sequence of solutions, then we converge to a unique minimizer of this energy functional capital phi that defines our problem. And we're actually also able to show that we get a monotonic convergence to that minimum value. And again, I won't go into the details, but essentially we're leveraging a lot of the analysis techniques that were used by some of the other researchers that I mentioned, like Sobolev and Leon in constructing this proof. Okay, so let me now show examples. And as I warned, this is going to be a little bit heavy on the examples, but hopefully they will be kind of illuminating. Before I get to the examples, let me talk about implementation. So for the quasi-static case, I'm going to show results for a code we have called Albany LCM. So what is Albany LCM? So this is an open source parallel C++ multiphysics finite element code. It's available on GitHub at the URL that you see here on the right. Some of its salient features are summarized here. So it has a component-based design that enables rapid development of new physics and capabilities. And the components here are primarily Trillino's libraries. These are developed at Sandia and also available on GitHub if you're interested. The LCM suite within Albany, which stands for Laboratory for Computational Mechanics, this is a suite that contains a wide variety of constitutive models that have been developed probably during approximately the last 10 or more years. And these range from simple linear elasticity all the way to very sophisticated microstructural models like crystal plasticity. And then the last thing I wanted to say here, so what turned out to be non-trivial for us in doing this implementation in Albany was how to do these search and interpolation from one domain onto the boundary of the other subdomain. And in particular, this is not entirely trivial to do in parallel, okay? And so for the parallel implementation, we're relying on a library that's called DTK, which stands for Data Transfer Kit. It's also available on GitHub. It's developed mostly at Oak Ridge, and it gives us a really kind of nice parallel, easy to use implementation for that search and interpolation piece of the algorithm. Oops, okay. So examples, I'm going to show 4 examples here. And these are going to go from, just simple verification problems just to kind of verify the method and reconcile it with some of our theory that I mentioned, and then go all the way to kind of production-like problems just to give you a sense of, where we're going with this in terms of using the method. For example 1 is really simple. So this is what I'm going to call the cuboid problem. We have the coupling of 2 cuboids with a square base. So these are shown in these images. And as these images suggest, we're going to play around with using different discretizations of the cuboids and also changing the size of the overlap region, which I'm going to call the overlap volume fraction. We're going to put a new Hookean type of material model, and we're going to pull on this from the top, so it's going to stretch essentially. And new Hookean, this is a a nonlinear elastic type of material model. The first thing I wanted to talk about is actually this picture at the bottom. So this is just giving you a flavor of how the Schwarz iterations progress. So initially you're going to have some noticeable error in the overlap region, but then as the iterations progress, this will eventually get corrected kind of as information propagates through the boundary between the different domains. So what we looked at here is convergence with the overlap and the level of refinement. So on the left, what we did is we fixed the overlap volume fraction, and we looked at different discretizations of each of the cuboids. So they were all hex discretizations here, having different resolutions. And what the picture here at the bottom is showing is basically errors in 2 subsequent Schwarz iterations, so that the slope is the convergence rate. So we're able to show that we get a linear convergence rate, and that's actually consistent with the theoretical result we have in the paper as well. About the convergence rate of the method. On the right, what we're doing is we're changing the size of the overlap region to see what happens with the convergence. We're plotting this convergence factor, which is kind of a ratio between errors in 2 subsequent Schwarz iterations. And there's a lot of points here, but essentially what this shows, if you kind of stare at this, you get a faster linear convergence as you increase the size of the overlap region, which again is consistent with you know, the theory and kind of what you would intuitively expect about the method. We also computed errors here. So these were with respect to a single domain reference solution, which is shown on the right. You can see displacement errors are basically machine precision. In the stresses, it's a little bit larger, but still quite small, 10 to the minus 13. So essentially, we're not getting any coupling error introduced by the method for this problem. So having done that initial really simple verification, let's go now to a more complex problem. So this is example 2. I'm going to call this the notch cylinder problem. So here's our geometry in the left 2 pictures. We have this notch cylinder. Again, we have a Neo-Hookean type of material model, and we're going to pull it from both ends. So again, it's going to stretch. And what we're going to do is we're going to make 2 subdomains. So the first one is the one that contains the notch in the middle. And then the second one is the one that is away from the notch. Let's see what happens here. So first, you know, how are we going to discretize these? So as you may imagine, you know, all the interesting behavior is going to be happening in this middle notched region. So we're going to want to put a very fine mesh here. And then we're going to put a TET mesh just to illustrate the fact that the method can couple different element types, and couple that to a very coarse hex mesh in the second subdomain. Okay, so let's see what actually happens. Oops, oh, that started earlier than expected. Here's a movie that shows you the solution. So on the left, we have the displacement magnitude. On the right, we have one of the Cauchy stress components. That's something we look at a lot in these simulations. And you can see we get a nice smooth solution without any noticeable artifacts. This, if you're wondering what this is actually just the bottom mesh peeking out from underneath the top mesh. So that's not an artifact introduced by the method. We can quantify this. So we computed, again, errors with respect to a reference solution on an all hex mesh that's shown here. That was relatively fine. The errors in the displacement were about 0.1%. And what's interesting is if you actually visualize the error, which is what this is doing, you kind of see that the bulk of this error that contributes to this number is actually not the coupling error introduced by Schwarz, rather it's geometric error. So basically the reference, this is a curved geometry, the reference mesh can better represent this curved geometry than either of these relatively coarse Schwarz meshes. So you're going to have geometric error kind of where the curvature is seen in the geometry, and that's not you know, specific to the Schwarz method. You would see that with just a regular finite element discretization on a coarser mesh. All right, so what about different material models? So I alluded earlier that we can couple different material models. That can be done under some conditions. So let me show that under in the context of a specific example. Here we're going to put an elastic material model in this region away from the notch, this coarse region, and then an elastoplastic material model in the region containing the notch. And this example has hex-hex coupling, but that really doesn't make a difference for the illustration. So essentially the main takeaway here is that if you're looking at using different material models, you need to be careful to do the domain decomposition so that the material models are consistent in the overlap region. Okay. So this is showing you two domain decompositions to illustrate this. So the one on the left is the the good one. Here the overlap is far from the notch. There's no plastic deformation in this case in the overlap region. The models are predicting the same behavior, and you get a nice smooth solution. On the right, whoever made this mesh, they put the overlap region too close to the notch. And so what happens is you get this little artifact there because the models are kind of contradicting each other within the overlap region, and that affects adversely the convergence. So this is just something one needs to be careful of with the method. And it's not surprising that you would see this because our theoretical result is for the same material model throughout. But I do think from some of our numerical tests that it can be extended to different material models if you prescribe some compatibility within the overlap region. So two more examples. This is kind of moving towards production. Example 3 is the laser weld problem, and really, this was created for several different reasons. So first, we have 3 subdomains in red, gray, and green. So this is just showing that the method is not limited to 2 subdomains. We're coupling a couple different material models here, isotropic elasticity and J2 plasticity. And then as you'll see on the next slide, another aim of this was to check the scaling of our method, the parallel implementation in particular, in the strong sense, just to verify that things are looking good from a scaling perspective. So just to keep this brief, so we're able to demonstrate we get about a 50% reduction in the model size relative to a single domain discretization for this problem while keeping the error at a fixed tolerance. And then, oops, too far. And then here's the strong scaling result that I alluded to just a few minutes ago. So we're looking at several different Schwarz discretizations. Scaled this up from 64 to 1024 cores. You can see for all of these, we get a near ideal linear speed up. And this is with our parallel implementation that relies on this DTK library that I mentioned earlier. So the last example, this is really kind of an example of a production problem. And this is courtesy of some of my collaborators, some of whom are analysts, Coleman Allman, Jay Folk, Dave Littlewood, and Guy Bergel. And I like this problem because it illustrates kind of an interesting use for the method, namely that the method can be used as part of a homogenization or an upscaling process to bridge the gap between microscopic and macroscopic regions, okay? And so the way that this problem works, so we have this tensile bar geometry. The idea here is Coleman and his colleagues, they embedded a microstructure within this geometry shown in the middle. The goal is to study strain localization in the microstructure. And essentially, within this microstructure, we're going to put a very detailed micro model called a crystal plasticity model. And then in the macrostructure, we're going to put a more kind of less fine-grained model called a J2 plasticity model. And the idea is you're not going to be able to afford to use this micro model and the corresponding mesh everywhere in your domain, in this problem and in many other applications, as you can imagine. So you want to somehow upscale this model to the coarser scale model. So you want to, what I mean by that is you basically want to inform your coarse model with that micro model information, okay? And so the way this was done in this particular case is Coleman prescribed an ensemble of uniaxial loads to the microstructure. There were 10 loads, and they're shown here in blue. And once he did the simulation, he was able to kind of fit this J2 plasticity model to these curves to perform the upscaling. Okay, so with that example, I'll kind of conclude the first half on the quasistatics. Let's see, I have about 15 minutes. So, okay, so that should be good. So I'll spend the rest of the time on dynamics, okay, which has been some of our efforts probably for the past couple of years after we got good results for the specific case of quasistatics. So, as before, I'll start a little bit with a kind of motivation. So, when we began this work for the dynamic case, we looked at the literature. We did come across some Schwarz-like methods for dynamics. The bulk of these methods were using space-time discretizations, where you treat time as an auxiliary spatial dimension. And so, as with everything, you have pros and cons to this. This allowed you to use different non-matching meshes and different time steps, like the picture here shows. But unfortunately, again, with our codes and the size of the simulations we're running, putting in a space-time method really wasn't feasible for us. So this led us to look at developing a dynamic Schwarz algorithm that would work with more standard discretization methods where you first discretize in space and then discretize in time. So let me show you the algorithm we came up with, and I'll kind of illustrate this through animations. There are several key ingredients. First is your domain decomposition. Again, you have this picture that you guys are probably used to by now with the circle and the square without loss of generality. The second ingredient is discretizations of each of these. So you're going to have spatial discretizations. You're also going to have temporal discretizations. So time integrators in each of these domains, which don't need to be the same. And actually, even the time steps don't need to be the same with this formulation. And then the last ingredient is shown in blue. And this is what I'll call the controller time stepper. And this is basically going to define a set of global time steps at which the Schwarz domains are going to get synchronized. And hopefully you'll see what I mean by that when I go through the actual algorithm. So here's how the algorithm goes. So you start by initializing your first controller time step, for in this case from T0 to time T1. Okay, you're going to start with omega 1. You're going to advance this from T0 to time T1. And note that in doing that, you're going to need information from omega 2 on the boundary gamma 1. So that'll require the spatial interpolation that I talked about earlier. But it will also require potentially temporal interpolation if the different subdomains are using different time steps. Okay, that's an important detail. Then you go to omega 2, you do the same thing. Again, you're going to need to interpolate in space and potentially in time from omega 1 to gamma 2. Once both domains have reached time T1, you check for convergence. If the method is not converged, you return to step 1 and you repeat. Otherwise, you go to the next controller time step and you go back to step 1 and you repeat. Okay. So the controller time step, this is just a way so you don't have to advance it all the way to the end before you check convergence. You can do this kind of incrementally. And I emphasize again that this lets you use different integrators, different time steps. You do need to do a little bit of bookkeeping to do this interpolation in time for the different time step case, but usually this is not too bad to do. What about theory? So we have some theory for the dynamic case as well. And this is from a paper that is currently under review that we submitted about a month ago to CMAMI. And it's kind of similar to quasistatics. So we're showing in the paper that basically the requirements for convergence is that the method will converge if your single domain problem is well posed and the overlap region is non-empty. You do have some conditions on delta T here. And so without going into too much detail, just to kind of sketch this out, the way we show this, we're looking at well-posedness by studying the action functional S, which is the integral of the Lagrangian for this problem over the space and time. We want this to be strictly convex or strictly concave for well-posedness. And we look at this by computing the second variation of the action functional. And basically what we're able to show is that if we use a Newmark time integration scheme, which is the usual time integration scheme we use for these dynamic solid mechanics problems, then this is how the second variation of the action functional looks like for the fully discrete problem. M is the stiffness, or M is the mass matrix, K is the stiffness matrix, gamma, beta are Newmark coefficients, and delta T is the time step. And basically, if you kind of stare at this for a while, you can see this can always be made positive by choosing a sufficiently small delta T. And it's a little bit less of a strict result, less of a strong result, I should say, than the quasi-static case, but it has the advantage that you're able to kind of check this a posteriori for a given discretization. And our numerical experiments that I'll show essentially suggest that usually your requirements on delta T for stability and accuracy will lead to automatic satisfaction of this bound. Okay. So again, I'll show examples. So I wanted to talk about implementation because I'll talk about two codes for the dynamic case. The first one is Albany LCM. So I talked about this already. The idea is that Albany LCM is kind of a sandbox for prototyping new methods in solid mechanics. And so once we've done that, we go ahead and implement the promising methods in our production code. And so that's this second code called Sierra Solid Mechanics. So what is Sierra? This is basically a mechanics modeling framework. It's a Lagrangian 3D code for the finite element analysis of solids and structures. Has a lot of different modules with different fun names here. We're using here two of them, Adagio and Presto, for quasi-statics and implicit explicit dynamics. So I should say we have the quasi-static method implemented in Sierra as well. Just happen not to show those results in this particular presentation. But for the coupling, we're using a framework that existed in Sierra called Arpeggio. And so this was a loose coupling framework that was designed for mostly multi-physics coupling, so doing thermomechanical type of problems. And we were able to hijack this to do the Schwarz coupling. And what was really a pleasant surprise was we actually didn't have to write any code to implement this method. We were able to just use this framework and essentially create input files for the Arpeggio framework to perform all the steps of the method. Okay. So I'll maybe speed up a little bit just to finish up on time here. 3 examples in this case, and again, I'll go from verification all the way to production type of problems. The verification problem is in Albany. We actually did it in Sierra as well, so all the examples were done in both codes, as it turns out. This example is elastic wave propagation problem. We have this clamped beam on the right. We're going to put an initial Gaussian as the initial condition shown in the blue color for the Z displacement. It's going to split up and kind of propagate and reflect from the ends, and you'll eventually get the mirror image, and you'll see that on the next slide. Look at 2 subdomains, one from 0 to 0.75, one from 0.25 to 1. Study all kinds of different discretizations, implicit, explicit, tet, hex. And even though this is a really simple problem that's effectively 1D, and it has an analytical solution, it's actually a really stringent test for coupling methods, because if you see artifacts, if your method introduces artifacts, you will see them on this problem. Okay. First I'll show results for all sorts of different couplings, implicit, explicit, hex, tet, but with the same delta t. So I have some movies here at the top, Z displacement on the left, Z velocity on the right. Red and green are the Schwarz solutions, and then there's a blue one here, which is the single domain solution. And as I run this, you should be able to see that we get a nice smooth solution without any noticeable errors or artifacts that you would see if you were to try other coupling methods here. Okay, and that's kind of an eyeball conclusion. We can also do a quantitative analysis here by computing errors with respect to the exact solution. And so these are about 0.1%, and you can show that they're comparable to a single domain discretization having the same time step and mesh size. What about different time steps? So in this example, we're doing the same problem. We're coupling an implicit stepper to an explicit stepper. We're using drastically different time steps, so 1e minus 2 in the implicit domain and 2e minus 7 in the explicit domain. So I have, again, the displacement, velocity, and acceleration. This is at a different time superimposed over each other just to save space. And you also have a single domain solution here, which you can't see because it's directly underneath the Schwarz solution. So again, we get a solution that's indistinguishable from the single domain solution without any artifacts introduced. So let's now show a couple of more realistic problems. So these were from our production code Sierra, and I'll speed up here. So this is the tension specimen. It's a little bit like the notch cylinder. So here's the geometry. We're going to use an inelastic J2 material model here. The material is aluminum. We're going to decompose this into 2 subdomains, one containing this gauge in the middle, and the rest of this is the second domain. Within the gauge, we're going to put a very fine mesh comprised of high-order tetrahedral elements called composite tet10 elements. These are special solid mechanics elements that were developed in our group. Couple these to hex elements. And then what's done here is we put a really slight imperfection exactly in the middle to cause this thing to neck as it's pulled from the ends, which is the dynamical loading that we're going to apply here. And so since this is not a solid mechanics audience, let me just explain what I mean by that when I say it's going to neck. So this is just kind of the expected result. So basically, this is your initial specimen. As you start pulling it, you're initially in this elastic deformation regime. So it's just going to kind of stretch like before. Eventually, you're going to get into this plastic regime where it's going to neck or get kind of really thin in the middle here. And then after a certain threshold, this is going to fracture, right? So let's look at the movie here that shows you the solution. Y displacement on the left, nodal equivalent plastic strain on the right. Nice smooth solution, and you get the necking behavior in the middle. This is all in about 3 Schwarz iterations per time step to reach conversions for this problem. This is a little bit more eye candy, so it's the same, oops, too fast. It's supposed to be a movie. Oh, here we go. Same movie, just different color bar, and you can see it from each subdomain's perspective. And then this is the Cauchy stress. We look at this a lot. And you can see the maximal stresses in the middle, meaning kind of this is where you're going to get the failure as you would expect. So the last example, this is kind of where I started, so I'll end with this as well. This is our bolted joint problem. So I think I already kind of motivated this, and this is really the type of problem where you're going to want this plug and play feature of the method to explore different designs for these different components that are being coupled. So here's our computational domain. On the left is an example of where you might find this in the real world. This was a lamppost, but for us, this is going to be maybe a nuclear weapons component, but I'm not going to be able to show that picture here. So you just get the benign light post example. We're going to decompose this into the bolts at the bottom here, and then the rest of this we call the parts. Bolts are discretized using composite Tet10 mesh, again, very fine mesh, coupled to a relatively coarse mesh of the remainder of the domain. We have a couple of different materials, and again, we have this inelastic G2 material model. So we're going to apply an X displacement from left to right. So here's the solution. So I'm comparing single domain to Schwarz. And I call this the backing into a pole problem. So that's supposed to be funny. I don't know if people are laughing, but so I came across a deformed configuration in a San Francisco parking garage. So that was kind of fun for me, probably not for whoever did this, which was not me for the record. But you can see the single domain and the Schwarz solutions are the same essentially. And you also get these, the physically expected behavior. You get this thing lifts a little bit, and here you have a lifting, and that actually happens in the simulation if you look closely. Nodal equivalent plastic strain in the bolts, that's something we like to look at. And again, the single domain compared to Schwarz. And this is showing you that kind of the failure is going to happen here in the bolts, where eventually I think the top part here would probably pop off. It's probably what you would expect. So what's very much of interest for the realistic problems is how does this perform? So we looked at convergence rates numerically. We get, again, a linear convergence rate similar to the quasi-static case for the method. And I think the most interesting slide is this one, actually. This is reporting some of the performance metrics, so CPU times and the average number and maximum number of Schwarz iterations for several discretizations of this problem. So the main takeaways, so you can see for the coarser version of this problem, what's really interesting is despite the method being iterative, it can actually be faster than a single domain run for discretizations having a comparable number of elements in the bolts, okay? And that's not obvious that it would happen because it is an iterative method. And so I think what happens is basically each of your single domain problems, they're easier to solve than your coupled problem. And that together with the fact that this is not converging in very many iterations is leading to an actual speed up here. Now, if you look at the second two rows, you don't see this here. This is a finer discretization of the bolts. Schwarz actually loses here, so it's slower. But I emphasize that even if the method is more computationally expensive for some problems and some resolutions, it may still be preferred for its ability to rapidly change and evaluate different engineering designs, which is our typical use case. Okay. And so, yeah, the other, I already talked about this, but it's interesting that even though the overlap region is really tiny here, so it's just this region around the bolts, we're still converging between 2 to 4 Schwarz iterations per time step. So I'll wrap up. I know I'm out of time here. So I talked about the Schwarz method as a means for multiscale coupling in a quasi-static and dynamic problems. The method achieves all these wish list requirements that I mentioned earlier on, so we're quite happy about that. And then we're still working on the method. I won't say a lot here, but essentially the main task that just started pretty much is we're looking at developing or extending the method to the case of mechanical contact. So trying to come up with a Schwarz-like algorithm for simulating contact to address some of the well-known challenges that arise there. For instance, accuracy of the contact constraint enforcement, dealing also with the multiple scales that are involved. And the idea here is to combine Dirichlet and Neumann boundary conditions in a non-overlapping fashion to try to do this. But we just kind of started trying to think of this, so it's still kind of very, very new. So, perhaps next time I present this, I'll have something to say about this. So I'm out of time, so I'll stop. So here are references. The red 2 at the bottom is our work, and the last paper is available. The preprint is available on my website, which is listed here if you're interested in checking that out. That's for the dynamic work. Thank you for your attention. Sorry for going a little bit long.
All right, thank you. Wow, that was great. Maybe we could just take one question. Otherwise, perhaps people can just maybe direct message Irina with any questions via the chat, or I'm sure she'd be happy to receive an email with any questions too. So, but does anyone have a quick question?